just so everybody's on board, so we all remember what we're going to be doing, we're going to be doing the Huffman encoding now. So we built the encoding table and we built the decoding table. The decoding table is interesting because you have to like walk a tree to decode it, whereas the encoding table is not, it's a map. So they're kind of like two different data structures. So to encode something, I need to have a data array and a bit index. If you exceed the size of the data array, that means your Huffman encoding is actually larger than the data itself. So I should probably throw like an error right there. That'd probably be a good plan to like just return an error encoding, like, sorry, this is just too big. You should just not, like, you shouldn't use this. That way I can always keep on using the same data over and over again, which means I'm probably also going to need an internal length. Because, I mean, you could technically cache this data so you're not recreating the data array over and over again. And I can always just use a Huffman and just be like, here's your encoding table. Here's the data, encode for me. And then it can just pipe it all into this little data right here. That's probably the way to do it, honestly. Probably the way to do it. All right, good. I think we're all on board. All right, so that's what we're going to be doing. Does your Git include work trees? The second part will include work trees. Second part's going to include work trees. I'm working on the second part later today. All right, for those that don't know, I released part 1 of the 2-part Git course on boot.dev, boot.dev/prime. If you want, the data, it's out there for free, for free. If you want to just look it over, you can have that. Bada bing, bada boom. Did you explain how Huffman trees work? Yes, I have a video on me doing a Huffman trees. They're very, very simple. Huffman trees are, you just build up the ultimate encoding for a tree. So if you had... we'll do a quick one over on this one. Let's say that I have the following data: AAA, BB, C, and D. It produces an encoding table that looks like this, which this probably doesn't make much sense for you, but what this means is that A is binary encoded 0. So that means it only requires one bit that's set to 0 to say that this is an A. B requires 1 0. D requires 1 1 0, and C requires 1 1 1. And there we go. We now have a beautiful binary. We now have that. So that means as I read, I can tell where I'm at by following a tree. So I read one bit, and I walk the table according to that. If I hit a terminal node, then guess what? That's a value that we need to report. That's a decoded value. And then we restart at the top of the head again. So decoding is pretty interesting. Decoding will be a fun exercise because it's a lot of tree walking in an array. And so there's definitely some like things we got to think about there. A lot of fun. There we go. Hey, Patino, Dev, appreciate that. Let's go. This is useful for me since I just learned about Huffman encoding yesterday. Nice, nice. All right, so let's start doing this. We're going to do Huffman encoding now. So I'm a little bit, I don't know how this is going to go. So let's see. We have a Huffman. Okay, good. So we have a Huffman, so we should probably just use that, huh? I'm gonna call. I don't know what to call this thing. I'm gonna call this one. Yeah, why not? Perfect. All right, so should be no errors. Awesome. All right, so we're gonna go here, and I'm gonna jump in here. So now I have this. This is my encoding and decoding. So we're going to first start by encoding. So the encoding table is how I decode. I should probably rename this to like decoding table, and this is my encoding map, right? So that means I should be able to go like this. Func, H star Huffman. I should rename those, and we probably will. I want to encode, and what I need from you is an iterator, right, which is going to be a byte utils byte iterator, right, which is just simply going to have a next. And that's that. So that way I know. And so whatever values come out of here, whether they're 16-bit values or 8-bit values, we just use those. And what should come out of here is probably going to be some sort of data, some sort of byte, right? I'm going to actually have this. And I'm going to re-return that result or an error. This feels good. I like where this is going. I don't know what's kind of happening here, but I feel happy about that, okay? I feel like this is the right... I feel good about this, okay? I feel good about this, okay? So we should have some errors, right? We should have this one. Let's see. Huffman encoding exceeded size. Wow, turn into Java here. Java new Huffman encoding has exceeded the data array size. Now, is there any other? Oh, let's see. Missing. Let's see. Huffman missing value. The iterator produced a value that is not contained in the encoding table. There we go. So those would be the two errors that we should encounter. Yeah, look at this. We are thinking, people. We're thinking. Remember, we're thinking here. We're thinking hard here, okay? And that's what I like. I like it. I'm ready. I don't really like the var. I don't really like that type of syntax. It's just not for me. It's just never going to be for me. You know what I mean? We're thinking, okay? So that means all I need to do is just produce an iterator or produce a bit index. So here we go. I'm going to go like this. Current val equals byte 0. Yeah. Thank you very much for that delicious raid. Oh man, we are in the middle of a heated competition right now. Okay? Check her out. She's great. Absolutely great. Closure raid. That's right, closure raid, looking like that. All right, so for those that just got here, we are doing Huffman encoding. Okay, that means we're actually going to take our encoding table and encode a binary array into a smaller binary array at this point, okay? So I'm going to be doing it by having a bit index and a data array that I'm writing into and a length, all right? So this is kind of important. All right. And so that means what I'm going to be doing is I'm going to be going through a byte array that you hand me, and then I'm going to be effectively shrinking it down by returning a slice of this data, which I think makes most sense for this. You hand me a byte iterator, which is going to be how you hand me out values, whether it's 1 byte or 2 byte values, or technically 4 byte values. I have no idea what your value size is, and I don't need to know. I just need to know that you can hand me an iterator and that I should have all of those values stored within a table. There you go. So that's what we're going to be doing. I'm pretty excited about this one. We'll see. Bit index is going to, this is where things get a little bit interesting because my bit index should be 7, right? Because that's the 7th position. Because if I shift something over 7 times, that puts a 1 into the 8th position, correct? Yes. Yes. 7 shifts is the 8th position. Huff on these nuts. That's right. Absolutely. So there you go. I think we're pretty much we're there. You're wrong about 0 indexing. I'm not sure which indexing that is. Got him. I know. We got him. Bench press. Let's see. Fit daddy first time in gym. What do I do? Bench press. Bench press. Easy way to go. Easy way to go. Oh, is this some sort of Lisp method? Are you lisping? That looks like a Lisp method. Right. Huffman encoding was a part of the Scala functional programming course I've done years ago, and it was so much fun. So I've never done it. This is my first time. Right? I've never done it before. Definitely a racket method. CDR. Yeah, CDR. Hang clean. Yeah, there we go. Okay, so there we go. So we're going to start with this. And what I'm going to do is I'm going to walk through these values and start writing in stuff. So I can go like this. 4. And I'm going to go value in. Oh, I can't do it that way, huh? This is where I really wish, I don't think you can, dang it. You can't really do this well in Go. I feel like building iterators in Go kind of sucks. Right. Res equals iterator. Next. There we go. So if we're done, well, this is where I wish we had a do while loop. Let's see, if done, then break. There we go. So we have our nice little size here. So now I'm just going to walk, and every time I get one of these values, I'm going to get the encoding, right? So I'm going to go like this. I'm going to go, let's see, encoding is going to equal h dot bitmap. Let's rename these right now because this is getting frustratingly bad to name these. And let's go like this, res dot value. There we go. If not okay, then return nil. And the error, of course, is Huffman missing value. There we go. We have a Huffman missing value. And now that we have, let's see, let's go right here and let's return out. And I'm going to have some sort of length, right? All right. For those that don't have the music, this makes literally no sense. If I breathe anymore, I'm going to pass out. Yeah, I know. Liked it. Yeah, this is a good one. I'm usually pretty happy with this kind of stuff and go. Okay, so we have this. Let's see. Hold on. We don't want to use len. All right. Let's see if I can do this one. Encoding table. And then this one is decoding tree. There you go. So I have my encoding table and my decoding tree. Yeah. All right. So we got our encoding. So our encoding is going to be our byte array. Now this, all we have to do is we just have to walk it. And it starts from most significant to least significant. So I have to write it in from most significant to least significant. And what I'll do is this, is that we'll always make the assumption that my byte index is valid. I like that. I like making the assumption that my byte index is valid. I like it. I like it. I like it. Okay, people. All right, so sorry, this will take a second to think through because I only have one try to get this, or I have 3 runs to get this right. 3 runs to get this right, or else, well, no. But look at that. I cannot believe how many people think I'm going to get this right first try. This is such a hard problem. This is like such a hard ass problem. All right, so we got our encoding table, which means I'm going to walk it from most significant to least significant. Go like this. Encoding. There we go. So I'm going to do something here. Shifts, and then I got to reset. If a byte, let's see, byte index minus. If byte index is less than 0, then byte index equals 7. I need to do something with this, right? I need to do something with that, and length equals, there we go. So now with that in mind, I'm going to actually have it start at 0, and here's the reason why. When we hit this, I'm going to write the current value in. I'm going to go like this. Current value, I'm going to go data. No, it's out. Length equals current value. Reset. This is looking good, by the way. This is looking good. I think we got this. And then I'm going to do the exact same thing down here, is that I set the last one. Ooh, there is that one edge condition. I need a dirty flag. There we go, right? Okay, so we're very, very close now. I believe in that. Making shitty programs. Yeah, what else do you do? President, can I come and work for you and just be your hype man? And maybe like $200K a year? Yeah, absolutely. That seems like a reasonable position. As a senior HTML engineer, I feel compelled to tell you that your code is wrong. Thank you. All right, so this is good. So now all we have to do is do the shifting part. Okay, so the shifting part should be pretty easy. I'm going to take the current bit. I'm going to, okay. Shifted bit. We should be able to go like this. I should be able to go like this. Current value equals current value or, yeah, bit shifted over by byte index. Correct? I think I'm right. I think I'm right. Yeah? What's your words per minute? About 120. I think that's right. I think I'm right on that one. I like it. I think, therefore, I am right. Yeah. How many story points is that? A lot of story points. All right, so we got our encoding. We got our bits. We've done all this. I actually think I've done this right. I want to say that I'm an actual genius. Yeah. I think that I literally think I just first tried that one. I like that I actually think I'm this smart. I'm not this smart. Okay, let's find out. Here we go. We're going to do this now. I actually think I did this first try. Test Huffman encoding. Okay, this is just ridiculous. I'm going to use our exact same little thing right here. I'm going to go like this. I'm going to go like this. Get frec, right? We need our frequency, right? Which is going to be a frequency, right? We just, here, let me just move over this. So we have our base frec. Because I'm tired of get frecked, son. There we go. All right, get frecked. Oh, what the freck? Freck you, son. Get frecked. Look at the big brain on Prime. Dude, I think I got this one. Okay, so we get the freck. We calculate the Huffman, which is now, we're going to actually rename, rename this thing Huff. Huff, baby. Yo, my name's Huff, daddy. And so now I should be able to take my Huff, and I should be able to encode. Okay, so now we need a new byte iterator. And let's create our own little byte iterator right here. And I'm gonna have it be like this. A. Now this is where I'm gonna intentionally add in worst possible case scenario, right? Because these are 3 bits, right? 3 bits of zero. And now I'm gonna go like this. C, which is gonna be 3 bits of 110, right? Which should cross byte boundary, right? This should cross byte boundary. So if I've done this, this is by far, like this is where any bug is going to exist. It's going to exist right there, crossing byte boundary and then properly being written in. Okay, this is good. This is good, people. Now, one thing I don't get with my Huffman encoding, I realize, is I'm not returning out bit length. I do need to return out bit length. I just do, because we don't know. Let's see, we also need an int. We need a bit length. Should I just create a... I mean, I could create a struct. I don't want to create a struct. You know what I mean? I don't want to create a struct. All right, so that means every time I do this, I go bit length plus plus. Every time I do that, I increment my bit length. Perfect. So that means we now know exactly how long our bit length is. Yeah. And that means our out needs to be up to our length. So that means we know how long our array is and how long our bit length is, so we don't accidentally go in. Technically, I don't even need to do that. I guess if I were to really do this, I could actually drop this entire thing and just have bit length come out, which would tell you how far into the array I wrote. I think that's pretty fair. And then I'm going to go like this. If length is greater than or equal to length of, I don't technically need to do that. Length of, what do we call it? Out. Then we have to return 0.Huffman encoding seed size error. Yeah. So I think I've covered all the cases here. Man, I think I actually got this. So we're gonna try byte boundary encoding byte boundary. So we're gonna have to create a couple tests here. So now, what is our data here? We're gonna go like this. Data is going to be a byte array. So this really should only have to be 2 bytes. So if I've done this correctly, I should just have to go like this, right? Yeah, should only be 2 bytes long, and this should not cause an error. Man, this is going to be such a rough one. This is such a rough one to get right. No error, right? No error. If I get this right, this is just ridiculous. Okay, this is actually ridiculous. Equal T, let's see, the bit length should be 369. Damn good time. Bit length should be 9. And our data should be equal to 6 zeros, and if I'm not mistaken, C is 11111, 6 zeros, so our data should be equal to 0x3, and then 1, right, it should be that, 0x3, and then 0x, just 1 bit over furthest on this side is which is what, 8? right? So if I've done this correct, that should be, it's encoding, right? All right. Do you guys think I got this? I'm not even going to pretend to understand what he's doing, bro. Yes, you are. All right, so here's the question. Can we all agree with this? Can we all agree with this? Just to like move this show along, can we agree on one thing? If I run the test and it doesn't fail, it doesn't count as a run, but the only programming I can do is add a new test. Because either I can write all 4 tests now, or I can write one test, make it work, write the next error boundary test, and make them work. Is that fine? I think that's a fair trade-off. Long as I successfully run, that's fine. Is that the test going to use a table that you preset? Fair enough to do your thing. Yeah, because I'm not writing new code. If I were to write new code, then that's a try. I'm not writing any new code. So there we go. So that would be the test. So this is where I would run it, but of course I'm going to add logging because remember, I only get a couple runs here. Okay. So I think this is right. I honestly think this is right. C should be, yeah. C should be 1. This. I programmed it as all 1s. I just wrote it as not all 1s. You know what I mean? I like turtles. Nice, Nintron. I like turtles too. And Ifari, thank you for that Twitch Prime. Brand new, babies. All right, so there we go. Let's go into here and let's start printing out the encode. So I'm going to do the following. I'm going to go format.printf. Let's see, I'm going to go Huffman res or iter, and we'll do one of those. And we're going to have a nice little iterator. We're going to grab out this one. I don't need to do this because this will automatically fail right away. So we don't need to really care about that one, but I do want to print out the encoding, right? Encoding is going to be the following. Encoding. All right, perfect. Is there a way to print out the binary of a value? Print out, I mean, I guess I could print out the hex, right? I could go to 2x, right? And I could go current val with byte index, this, with bit count, that. So I'd go like this. I'll do bit length first, and then I'll go byte index next, and then I'll do current val. Right? That seems about right. That seems about right. I like it. I like it. I like it. I'm going to indent it just a little bit. And I'm going to give a quick reset. Right, we're going to do a quick resetting. And the resetting is going to, then I'm going to put in, I'm going to print out the out array. Yeah, and then down here, I'm going to go like this. Done, and I'm going to print out the out array. Okay, good. Now let's add some new lines. Make sure every place has some new lines. Very, very simple stuff. Okay, so I like where we're at. Everyone agree this is nice? And then we'll go like this. Format.printf. Done. Yeah? Yeah. Everyone's good? I think this is good. So instead of AAA being 24 bytes, no, 24 bits, you can encode it in just 3 bits. Correct. That's what makes Huffman so good. So you get the idea. So technically, for me to be able to store AAA, right, you get the idea, AAA, it'd require technically 8 bits per character. But because my Huffman table only has 4 characters that it has to encode, it's able to encode this in 3 bits. Or since you can't send down 3 bits, it has to encode it in 1 byte. You have to always go to the byte boundary, right? That makes sense. You can't just be like, I'm sending down 3 bits. It just doesn't work that way. So that means you can write you can write a lot of data really, really small if you don't have a lot to encode. The thing is that your encoding of the Huffman table takes, hey, I hope you really appreciated the, what's it called? I hope you really appreciated the, what's the big W there? The internals. I think the internals really made people, I think that made people very happy. Is that why you need bit length? This is why I need bit length. Precisely. That's exactly why I'm keeping track of bit length, because I want to be able to say, this is how many exact bits are within here, because I could be somewhere in the middle of a byte, and then it could have junked data that actually produces real values due to the Huffman encoding. So right now, I don't want that, right? I don't want that at all. All right, so there we go. I think this should work. So I'm going to run this now, and we're gonna do our agreed thing, which if I run this and it just successfully passes, then it doesn't count as a turn, and I'll write the next test, one of the error boundaries. And if that passes, then I'll write the next error boundary, and we did it first try. Else, if it fails, I will have to figure out by just the logs. I am an effing genius. Look at that hex. Literally first tried that one. That was as first tried has ever been first tried in the actual effing universe. Okay, genius. Thank you, Adriel. That was as first try, no deaths. Yeah, that was a perfect run. The Tomogen, that was the Tomogen. We just Tomogened that one. Look at that. You can even see it encoding, right? So here's a iterator. Look at that. You can see this. The iterator is not done, and it's 65. It's not done 65. Current value. You can just watch the current value bit index. Keep going. Nothing's being written until this last one right here. Look at this. We got ourselves a 67, which is the C, which our iterator's done. Our encoding value's 3 ones. We write in a 1. We write in a 1. We now have to reset. We are resetting. We have a 3-0. Oh my goodness, look at that. We got a hex 3, which is the equivalent to what I just wrote right there, 0-3, and then an 8-0. You can see right here, current value. Let's go. Done. That feels good. I'm not gonna lie to you. That felt really effing amazing. Okay, that was like as first try gets. Okay, so let's do a byte boundary. Right? Let's do one that crosses how big my byte array is. So if I go like this, let's see, what do we want to listen to next? I really did like that previous one. Lithium, is it because I got it right first try, Lithium? Is it because I got it right first try? You little rascal. I appreciate that. I do. Because those were celebration shots, dude. I'm not gonna lie to you right now. I'm like, I'm high as shit on life right now. That was the greatest feeling ever. I just had the greatest dopamine hit I've had programming in probably 4 years. Thank you very much. It felt so good. Too loud for you guys. New ball when? I don't know when, but I need to do that. Getting high off of dope on the stream, I am, dude. It was a pleasure watching you shoot up, dude. Thank you. This was as good as it gets. Okay, so we're gonna go like this. We're gonna go testing encoding. Let's see. Encoding too large, right? Never had that one. I've never had that problem. Too large. Is it too large or is it too large? Too large. Is it two O's or 1 O? I never even know. YouTube guy sucks, by the way. Yeah, I know. 2. Okay. Yeah. So we're going to do that one. So this one should cross the byte boundary, which we should have an error, right? All right, so I should prove that it's an error. Can I assert on error type? Is there like an error type? Error is? Yeah, so I should have an error is, right? So that means my error is should be Huffman, right? It should be exceeded value, right? So if I've done this correct, I've handed in a byte array of size 1, and I'm encoding into 2 bytes. Thus, my encoding is too large. By the way, if I ever have the chance to pick my own walk on stage song, you know for a fact it's this one. It's such a little banger. Tell me that's not just a banger. What's it called? I don't even know what it's called. Melodic techno and progressive house DJ mix number 4 at Dubai. All right, dude, it's such a banger. Such a banger. Dubai mentioned. All right, so we have error too large. So if I've done this one correct now, we should pass again. Let's go. All right, what's the last error? The last error is unrecognized character. Right? Unknown car, right? It's what's it called? Is it Huffman missing value? Yeah. I'm gonna let's rename this thing to Huffman unknown value. Perfect. Huffman unknown value. Let's go. Let's go. Wait. Yeah. Thank you. Thank you. First tried everything. First tried that whole son of a bitch. Let's go. Everything just got first tried. Everything just got first tried. All the way through. We bit and coded the shit out of that one. Oh, baby, that feels so good. Let's go. Let's go.